You're reviewing for a final. You're like, what do you want to go over? Of the whole course, people might say, can we do that domain and range again from chapter 14? Oh yeah, we can. There's a radical or a natural log. But when there's one more thing from this sheet, it doesn't say level curves. What does it say? Those are functions of x, y, and z. All right? Those are functions of x, y, and z. And they want you to find the what? Describe. Oh, good. We don't have to draw these. Okay? Describe the level, not level curves, but level what? Surfaces. And that's not a typo. But they do put this, at the end of 14.1, level surfaces. When they ask for that, then you have a function of x, y, and z. Oh, we get it. Now there's a third level. A function of x and y, you can have level curves. Take those level curves and you build something three-dimensionally. A function of x, y, and z, you have level surfaces, like a family of what? Spheres or something. But then, if we did this part, that would be what? Fourth dimension? And fourth dimension is just so hard to even try to grasp or just sketch that. We won't be sketching it. Okay? Yeah, you're like, wow. Because you'd be going into fourth dimension there. All right. But now, let's look at the first one. What do they got? X plus 3y plus 5z. Remember, we just got to put down a word or a couple words just to describe this. We'll do each one of these. These go quick. Describe the level surfaces. Surfaces. Make sure you see that word surfaces. Because we're not going to say, oh, something like this. I wouldn't say, oh, they're parabolas. Parabolas aren't cylinder, surfaces, right? It's got to be something three-dimensional. So what do you think the first step is? Let z equal to, and you go, there's no z this time. We'll let the function of x, y, and z be the k. If you want to make up another letter for this, I don't think you can. You can call it w. But the function of x, y, and z, let that be a k. So pretend this is a k. This is how we do it. Let this be k now. Now think of that family of all those surfaces. What are they? What would be the surfaces? K equals x plus 3y plus 5z, and you got different k values. K can be a 1, k can be a 2, k can be equal to -1, -2, a bunch of what? A bunch of planes. Bunch of planes. I'll put family of planes. See, you get a family of planes. Love the surfaces. Alright? Yeah, these go pretty quick. How about what's the next one? X squared plus 3y squared plus 5z squared. This is why section 12.6 was so important. We now have to recognize this stuff. Those surfaces from section 12.6. X squared plus 3y squared plus 5z squared, and they said for k greater than 0, right? So let this be a k. So close. Spheres need to be perfect, all the same coefficient. So the football thing, what do you call it? An ellipse? Ellipsoids. So this would be a family of ellipsoids. Alice, good job. Because Nate, she goes spheres, and then she goes, wait a minute, they want to be spheres because that's a 1, that's a 3, that's a 5. She goes, oh, ellipsoids. Footballs. Blimps. Cool. X squared minus y squared minus z squared. And he said for k greater than or equal to what? Section 12.6. I see two minuses. Hyperboloids of how many sheets? 2 sheets. So it's a family of hyperboloids, you can abbreviate. Family of hyperboloids, put how many sheets? So I'm going to put 2s. It's a family of hyperboloids of 2 sheets. This is the one I need you to be careful on the problem set or on a test. You can get people. Function of x, y, and z, y squared plus z squared for k greater than 0. Oh, it happens all the time. Like on a multiple choice and people choose circles. First of all, a surface is not a what? So a circle is not a surface, right? Right? So what are these? Think of this. K, there's only two variables in there. What was going on in 12.6?
Cylinders.
They're cylinders. Very good. Circular cylinders, right? They're centered on which axis? Which letter's missing? I mean, if you wanted to go further, but we can just say a family of cylinders or a family of circular cylinders. If you want to go even further, you can make it's a family of circular cylinders all centered on the what? X-axis. And now you're really thinking fourth dimension here, because that's what you're thinking. But it's a family of them, right? It's a family of them if you want to try. Now sketch it. What is it? They're all cylinders, concentric cylinders. They're all inside of each other, right? There you go. No, I'm not going to say it. But anyway, right. Yes. Family of cylinders centered on the x-axis. Hey, cool. Great job with this. Hey, I'm not going to pass this out. 1, 2, 3, 4. We're now going to do section 14.3. So once again, it saves time that you got a worksheet with a table. You have to copy the table. I'll put the table on the board, but you don't have to copy the table from the board. It's already there. We can work with this. These are called partial derivatives. You're welcome. Partial is a great section. You're welcome. We'll spend a good amount of time in this section. No rush for this section. There's 20 things. We're going to find partial derivatives, but we're going to find them from equations. We're going to find partial derivatives from graphs, from level curves. We'll find them from three-dimensional graphs. We'll find partial derivatives. We'll make sense of what they are. So there's different ways we're going to find these partial derivatives. Let me write this down right here. This is in section 14.3. Partial derivatives. All right. So, my first example, how about this? Function of x and y equals x squared y cubed. And you bet the first thing you saw in here was a table, right? We'll get to that table in a moment. I just want you to see how cool partial derivatives are. What's this variable z? We're going to find partial derivatives. So we can find the partial of f with respect to x. Let me read that to you again. This is going to be the partial of f with respect to the letter x. So what you do is, you differentiate everything here only with respect to that letter x. That means you're going to hold the y constant. Let that y be constant there. What will you get for f of x? Well, let me get this out of the way. I apologize. What will be fx for this problem? What will be the partial of f with respect to x?
2xy cubed.
So you said this would become 2x, but they held the constant right next to it, multiplied like it was a 5, and they got 2xy cubed. Good job. Hey, is there other notation? Yeah. Do you remember back in Calc 1 when you were like df, dx, derivative f with respect to x? We can do that here. We use delta, so the d is really a delta. Delta f, delta x, if we want to put that, but it's another notation. Oh, delta f. But you'll notice even in the textbook, they use that Greek letter delta there. Looks like a D, just write a D if you want. It looks like a D. I was wondering if you could find, oh, and another thing, sometimes they write this. It's the partial respect to x of the function of x and y. They might put the function of x and y still next to it. Right? Or here they might write what? Delta f, delta x, and then next to it put the, and you're getting this solution. But just like, remember, you sometimes wrote f prime of x, but sometimes you just put a y prime. This is like just putting the y prime. So, I use the easiest notation, which would be this. Can you find that? That would be the partial derivative with respect to what?
Y.
Y.
So 3y squared x squared.
Yeah, and they call it the first partial derivative. Because in a second we'll do second partial derivatives. So the first partial with respect to y, I get
3y squared.
3y squared to the x squared stays, and I'm going to go in alphabetical order. 3x squared y squared?
Mm-hmm.
Okay, I'll get this out of the way. What the heck is this? That's called a second partial derivative. You got it. To get there, she goes, you got to go through here first. So the first thing you had to take this and take the first partial with respect to x. Now you're going to take the derivative of this expression right here with respect to what?
Y.
Y. So what is the second partial with respect to xy right there? What do you get? 6xy squared. What they did, they differentiated with respect to y, this thing.
Mm-hmm.
Right? And they kept the x constant. True. And on that note, can you all find fyx? So in order to derive all this with respect to x, keep y constant.
6x.
Now this is interesting, I'm getting the same one.
6x y squared.
Interesting, they're both the same. Do you think that happens every time? It does. And there's a mathematician, you know, whoever comes up with first gets the name to it, like Pythagorean theorem and stuff, although Pythagoras was not the first one to prove that. Other cultures have done it. This Clairaut's theorem says that fxy will always equal what? Fyx. If, you know, as long as they're continuous functions. As long as they're continuous functions. Which you can even, feel free to read about that in the textbook. No, fxx does not equal fyy, but I was just curious, can you get fxx? So what's fxx? You'll notice it does not have to equal fyy. What's that? fxx? 2y cubed. You want to do fxxx? Or 3 x's? Third partial derivative? 0.
When you're doing fxxx, are you considering from the second one or the?
That's right. So I'm going to start here first.
Okay.
So it's like, this came from here, right?
Uh-huh.
To do this, I have to take the derivative of this expression partially with respect to x.
Okay.
They call it a second partial derivative. So you have to use this. We differentiate that with respect to x, and we just got the what? 2y
Okay,
cubed.
got it.
Now that you say, all right, you're like, okay, I got to take this expression and take the derivative of that partially with respect to x. They call it a partial derivative. Which you get what?
0.
A constant. Very good. This is equations. But you know, it's like, you go, yeah, you gave me a simple one. What about one with radicals? What about one with a sine or a cosine? We'll get into that. We'll get into that. We'll get into those later. We'll practice them. I have tons of practice problems. You can kind of practice on that. I got another worksheet. Okay, what's fyy? I'm just curious. Fyy would be 6x squared and then just a what?
Y.
A y? Hey, but I'll go back. Isn't this a three-dimensional graph? So you're like, well, what is that geometrically? What is this geometrically? A partial with respect to x would be the slope at a point in the direction of the positive x-axis. It'd be the slope of this. It's a surface, right? The slope of the surface, you know, any particular point that you plot in the direction of the positive x-axis. What's the partial with respect to y? First partial derivative. Because isn't that, remember back in Calc 1, isn't derivatives just finding slope? Slope of a tangent line. So it'd be the slope, fy. Partial with respect to y would be slope in the direction of the positive y-axis. You can find this at any point. Now, we used to say slope of a tangent line. Now I could say slope of a tangent plane to the surface. Do you follow me?
Mm-hmm.
But this is what this stuff is geometrically. Cool section, because now we're starting to think, ooh, we can take surfaces now to get a slope in any direction. Is where we're going, right? Before we were just kind of stuck in two-dimensional space going, oh, there's the curve, get the slope, right? Over here, get the slope. Now we're talking about a surface. You go to the point, you go, I can get the slope in any direction. But right now, we're only doing the direction of the x-axis or the y-axis. In Calc 1, what did second derivative represent? Concavity, right? Concavity. So now you're thinking, oh, I can take a surface and think if the surface is what? Concave up, like a cup, right? Or maybe concave down, like an upside down trout, like a surface. So that's what's going on. You go, oh, when you have like an fxx. And we'll talk about, I got some practice problems like that. I had to put some images on here that were three-dimensional, but we'll still be able to look at it. But what we're going to do right now, everyone, we're going to find partial derivatives from a table. We did it from equations, right? But just briefly, I gave you a simple equation. We're going to want more advanced stuff in a second. But now we got that down, can we find partial derivatives from tables? How do we find a partial derivative from a table? And you bet. Eventually we're going to find a partial derivative from a three-dimensional graph. So when I have a table here, and let's see what we got here. V, what's V stand for?
Velocity?
Speed, okay, that's the speed. What's T stand for?
Time?
T is the time duration in hours, and they said H is function of V and T. Boy, multi-variable function. And H represents the height of what? Wave heights, right? Cool. These are wave heights. So these represent wave heights. Here come the wind speeds. Oh, and this is the V. And I'll put these down here. What do you got? 20, 30, 40, 50, 60. There's a nice table here, right? I'll come across here and go like this. That's why I want to give you sheets. You wouldn't have to copy this. What's those times? Now there's the wind velocities. Now what's the time duration? The wind's been blowing for what? Let's see. 5 hours, or 10 hours,